Swayam Prabha. Digital India. Educated India.
So today we are going to discuss the duality concept in linear programming, particularly the examples. So we have already understood the duality concept, and we have also seen various theorems connected to the duality concept, and we have also solved a few examples. Now one or two more examples we shall again discuss, which are going to be important in the concept of duality. So as you already very quick recap about the complementary slackness theorem, which we have in our last class, we have already seen that suppose the primal is of the form maximize z equal to cx, subject to ax less than equal to b and x greater than equal to 0, which is the maximization standard form. Then the dual will be minimize w equal to yb and subject to ya greater than equal to c and y greater than equal to 0, which is the minimization standard form. Now this primal to dual conversion is symmetrical because if you take the dual of the dual, you will again get back the primal. So primal to dual and dual to primal conversion is symmetric in nature in that sense. And here also please remember that x and b, anything that is underlined, they are column vectors, and the remaining variables, that is c and y, they are row vectors, and a is a matrix which is of a certain dimension, which is about m into n, where m is the number of resources and n is the number of unknowns or decision variable x. Now if x0 and y0 are feasible for the primal and the dual problems respectively, then they will be optimal only if and only if y0 a minus c x0 plus y0 into b minus ax0 equal to 0. So that's a matrix equation, and essentially this y0 a minus c is nothing but the slack of the dual. Basically it's a kind of surplus variable. When you deduct ya minus v0, let us say, equal to c, so that would be the form for v0. And here if you put ax plus u0 equal to b, then this should be the form for the u0. So exactly that's what we have written in our next slide. And in a simplified form, the above expression comes to v0 x0 plus y0 equal to 0. Now these equation can only become 0 only when individually all the components of vj xj and yi ui, they are all become equal to 0. Otherwise this total expression cannot become 0. That's not possible. So this is what has been written here in the complementary slackness condition, that vj0 xj0 equal to 0 and yi0 ui0 for all I equal to 1 to m. All right. So that is usually called the complementary slackness condition, which is a special case of the complementary slackness theorem. Now, what that result actually tells us, these results basically tells us this, that if at an optimal point the primal slack vanishes, that means since the primal slack into the dual variable is 0, so if the primal slack becomes 0, then the dual variable will be there. It will assume some value. On the other hand, if the primal slack exists, then the dual variable value has to become 0. And same thing about the primal also. So if the dual slack vanishes, the dual constraint turns to equality, then the corresponding primal variable will be existing. All right. So these one second only. So these facts are very important in the sense that they can be used in solving interesting problems, particularly the network problems, which is also we are going to discuss. Yes, tell me please. So today again we are going to take one or two more problems, and we are going to discuss further onto the illustration of this particular important concept, right? So here is the problem, and the problem is like this: a person is engaged in buying and selling of identical items. He operates from a warehouse that can hold 500 items. Each month he can sell a quantity up to the stock at the beginning of the month, and each month he can buy as much as he wishes, so long as his total stock does not exceed 500 items. The items he buys gets delivered to him at the end of the month. If his current stock is 200 items, find his optimum buying and selling pattern for the next 3 months. For the next 3 months, the item cost and prices are as follows. Month 1, month 2, month 3, cost is 27 per unit, 24 per unit, and 26 per unit, and price is 28, 25, and 25 per unit respectively. So you see what is happening. He buys in each month at these costs, and he sells at these costs, these prices. So that is what he does. He buys and puts it in a warehouse. The warehouse is having only 500 capacity, and he has 200 items in the beginning of the first month. Now you tell me, by reading the problem, what happens first, the sale or the buying? Please understand this, that he is selling at the beginning of the month. Is it all right? And thereafter he can buy as much as he wishes, but his stock cannot exceed 500 items, because that is what is the limit. Is it all right? So if suppose his current stock is 200 items and he sells them, then he will be able to purchase only the remaining item only. So that means 500 items he can purchase. Okay. Now here one thing you must remember. Just one sec, I'll answer your question. You see these kind of problems. One thing you must always remember. Say for example, originally the problem was about 6 months. So I have reduced it to 3 months only. See, it doesn't matter whether you have 5 months, 6 months, or even 12 months. It's a continuous process. So what we usually do for solving problems, we just define a certain horizon, because ultimately you have to calculate up to a horizon. So there is always going to be some kind of horizon effect. So that we have to forget, because otherwise we cannot solve these problems. Is it not? So horizon effect means that whatever you have towards the end, if you sell that entire amount, obviously you get more profit. But then it will have an impact in the next period. But since there is no next period, we are not bothered in this particular problem. So those kind of things are always there. Please remember, it's a continuum. This is not, it keeps happening. We started with 200 items and we are going to do only for 3 months. We want to know how much he should buy on month 1, month 2, and month 3, and how much he should sell on month 1, month 2, and month 3. Yes, so there was some question. So that's what is the current premise, and these are the unknowns. So let us assume that we have 6 unknowns: x1, x2, x3, and y1, y2, y3. We say that x1, x2, x3 are the items bought by the person in these 3 months, and y1, y2, y3 are the items sold by the person in these 3 months. So how are they related? You can do a pictorial representation of his buying and selling behavior. So you see, initially there is a stock of 200 item. So he can sell, let's say, y1 amount. Now after that, he can buy 500 amount maximum. So these are maximum values. It's not that he has to sell 200. It depends on the problem. And after that, after the second month comes, again he can sell y2, and then he can buy, then he can sell, and then he can buy. So this is how the things are happening, and usually this is the timeline and based on that, these kind of financial computations can actually be represented. And sometimes these problems are more complicated because there is also time value of money, is it not? So when there are time value of money, we have to get everything to the present value by discounting the interest rate. Now here we are assume that there is no such thing. There is no time value of money and there is no inflation or any such thing. So that we need not worry at all. Right. So having said that, and these are the unknowns, can you tell me the constraints? Can you tell at least one constraint by looking at this pictorial representation? That means y1 should be less than equal to 200, is it not? Y1 should be less than equal to 200. Right. So that is one constraint that we can easily identify. Right. Now, see, this is exactly what we have revealed. Now, y1 should be less than equal to 200. But what happens in the beginning of the second month? What happens in the beginning of the second month? Y1 plus Y2 is the amount that you have sold. Is it not? You see, if I bring everything at the beginning, see, in the beginning we have a stock of 200. All right. Now, what is the change in stock? The change in stock is Y1 plus Y2 is the total sale up to this point, and you have purchased an amount of X1. So, if I bring back all that has happened in today's date, then till the beginning of month 2, then y1 plus y2 minus x1, that is what has happened, is it not? And that should be less than 200. Please, all of you, please check whether you are able to understand the second constant, yes or no. You see that first month how much you can sell. It is, you said very clearly, 200. So y1 should be less than equal to 200. So this condition was very easy to understand and everyone said this. But if we extend this particular constraint, what has happened till the beginning of the second month? We have total sold y1 plus y2, total purchased x1. That means y1 plus y2 minus x1 is the net change, and that is the net sale. That is the, forgetting that buying part, that is the net change in the stock. So net change in the stock up to the beginning of the second month is y1 plus y2 minus x1. Now that net change has to be less than 200 because you started with 200 irrespective of their values. Is the second constraint clear now? Think clearly. If you think clearly, you will be able to understand that why, the total change that happens from the beginning of the first month is about the selling behavior is y1 plus y2 minus x1. That is the net change in stock, and that net change in stock has to be within 200 because that is the number of items we had in the beginning. Clear or not? Is anybody having any doubt in this particular thing? Okay, so please think over. I mean, this is not a difficult constraint to understand. That is what it is. And if we extend it further, you will then get y1 plus y2 plus y3. That is the total sale over the 3 months, and x1 and x2, which is the total purchase. Because up to this point we are calculating, not the what you buy towards the end, up to this point, then that also has to be less than 200. So that gives us the selling constraints. So next comes the buying constraints. Now, can you tell me what is the buying constraints in the very first month? What is the buying constraint? What is the stock change up to this point? So you see, this is the buying constraint, x1 minus y1 plus 200. So up to this point, if I see this line, that is the end of the first month, then from a buying point of view, you have purchased X1, you have sold Y1. So X1 minus Y1 is the net that is available, and you already had 200. So if you add that, that is X1 minus Y1 plus 200, that has to be less than equal to 500. Is it not? So net change is purchased X1, sold Y1, you already had 200. So that should be less than equal to 500. So simplifying, you get x1 minus y1 less than equal to 300. Now, if you simply extend it up to second month, then x1 plus x2 minus y1 minus y2 plus 200 should be less than equal to 500, and which also gives us x1 plus x2 minus y1 minus y2 should be less than equal to 300. So that is the second constant also we get by the same extended logic. And then x1 plus x2 plus x3, that is at the end of the month, that is the total amount purchased, and y1, y2, y3 is total amount sold over all the entire period, plus 200, that should be less than equal to 500. Therefore 200 cancels, and this part we get again less than equal to 300. So you see, from the buying and the selling perspective, we could get the 6 different constraints by this kind of calculation. So my request to you now, to can you also put the objective function? What should be the objective function for this particular problem? So to understand the objective function, you have to go back to the table, which is the 3 months, the item cost and item price. The item cost is for purchasing and item price is for selling. Is it all right? So what should be the objective function? Not y1, y2, 28 y1 plus 25 y2 plus 25 y3 minus 27 x1, 24 x1 and 26 x1. Right, so this is this is exactly what it should be. The objective function, maximize z equal to 28 y1 plus 25 y2 plus 25 y3 minus 27 x1 minus 24 x2 minus 26 x3. Right, so this is how then the total problem is now written. All these things now, since these are all real quantities, x1, x2, x3, y1, y2, y3, they all must be greater than equal to 0. Isn't it? They cannot be less than equal to 0 because they are real quantities. So now this is the objective function we have already understood. There are some selling constraints and there are some buying constraints, and these are the decision variables. And these are the non-negativity constraints. So this is how we can formulate the primal problem. So primal problem is formulated, and we have already come to the first part of the problem is done. Now question is that how do we solve this particular problem? We can always solve this by the simplex method, is it not? So in that case, we need to take 1, 2, 3, 4, 5, 6 different slack variables. Already we have 6 variables, so it will be a 12 variable problem. You see, this is simple problem, very simple problem. I told you the original problem was having 6 months, right? So if we had 6 months, then 6 plus 6, there would have been 12 different constraints. And 12 constraints, additionally there will be 12 slack variables, so there would have been 24 different variables we had to handle. Even then, that's not very much. In real problems are having hundreds of variables. So nevertheless, this is not a very small problem. So solving by hand is not a very good idea, but you could easily use some kind of software package which you can use, and you can put these things and you can get the answer, right? That is definitely possible. All right, but what we want to see here, that is there a simple way by really taking its dual, and then from that dual, can we make some interpretation and even solve the problem, right? So just spend 1 or 2 minutes to write the dual of this problem. Let us assume that we have 6 dual variables as u1, u2, u3, and v1, v2, v3. All right. So what should be the objective function of these dual problem? So 200 within bracket u1 plus u2 plus u3, and plus 300 within bracket v1, v2, v3. That should be the objective function, and it should be one of minimization. Now, since all the constants are non-negative, in the dual problem, all the constants will be greater than equal to type. Now, you can see that these u1, that is that first variable u1, which is with regard to this. So what could be some constants with regard to, let's say, first you can see the y1. Yes, so you see in these first three, y1 u's are positive, and in the last three the u's are negative. So that means u1 plus u2 plus u3 minus v1 minus v2 minus v3 should be greater than equal to 28. All right. So all of these we can try to do, and let us say these are the 6 dual variables u1, u2, u3, v1, v2, v3, and from various calculations. So let us see if we look at from y2 point of view. So y2 should be u2 plus u3 minus v2 minus v3. Is it not? That should be greater than equal to 25. So let us see, this is how the dual problem is now formulated. So please convince yourself, the primal problem is also here side by side. So look at them together, and please convince yourself that the dual problem indeed is a formulation of the primal problem. Please look at it carefully. Are you convinced? See, from if you take these y1, then u1 plus u2 plus u3 minus v1 minus v2 minus v3. If you take y2, u2 plus u3 minus v2 minus v3. If you take y3, then u3 minus v3. Then if you take x1, then initially they are all minus. So minus u2 minus u3 plus v1 plus v2 plus v3, and minus u3 plus v2 plus v3 and v3. So you see we get a set of 6 different constants which is greater than equal to, and we also have the non-negativity constants. Now there is a difference between the primal problem and the dual problem. The dual problem, one good thing is about this dual problem is that, look here, first of all the variables are greater than 0. And it's a minimization problem, which is very clear cut that first of all, V's have more impact than U's. So if there is a conflict between U and V, that we have to reduce V first. That's one thing. So second thing that we know, that the values of the U's and V's should be as low as possible. Is it not? So all the variables should be at their lowest possible level. Now, one thing can you quickly see by looking at these 6 different constants, that the lowest possible value of V3 is 0. Please look at this last constant. V3 should be greater than equal to minus 26. So you see, if V3 cannot be negative, it is greater than equal to 0. So by inspection, you can easily say that lower bound of V3 has to be 0. Is it not? V3 cannot have a value which is low. See, now you see this kind of solving by inspection is possible, not everywhere. It is possible in this particular problem because it's a minimization function first of all, and here there are no negative terms, all are positive terms, and therefore we can straight away by inspection we can try to get a solution to the U's and V's. So from 6, can you see that we can really calculate V3 equal to 0. So because there are minimization problem and there are non-negativity constraints and the objective function doesn't have any negative term, so very clearly we can say that V3 should be equal to 0. Now go to 3. In this 3, U3 minus V3 should be greater than equal to 25. Yes or not? So since V3 is 0, then U3 should be greater than equal to 25. That means the maximum possible value of U3, I mean minimum possible value of U3 will be 25. So like this, you can actually, try to get the smallest solution of this particular problem, and you come up with U3 equal to 25, then you go to 5. Now already you know U3 which is 25, already you know V3 which is 0. So from here we can compute V2 equal to 1. So progressively you convince yourself that this solution set that U1 equal to 3, U2 equal to 1, U3 equal to 25, V1 equal to 0, V2 equal to 1 and V3 equal to 0 are going to be the smallest possible solution. You see, you can also have a slightly different variation like U1 equal to 1 and U2 equal to 3, which will also solve the purpose. And there is no change in the minimization. But nevertheless, you can actually do such calculations. Yes, is there any question? So this is how, so what exactly I am trying to tell you, that once we formulate the dual in this particular form, the nature of the dual problem is such that we can find out the solutions of the dual problem by inspection, and that solution should be the smallest possible solution, because after all it's a minimization problem, and the nature of the problem is such that we could solve the dual problem by the inspection method. Fine. So we found the dual solution, which is the value. Now what you can do, you can actually put this in the constraints, and what interesting thing you find by putting these values, the constraint 1, constraint 2, constraint 3 and constraint 5 have turned to equality. Is it not? Because look here, if we put U1, U2, U3 as 3, 1 and 25, we get 29. And V1, V2, V3, 0, 1 and 0, so we get 1. So 29 minus 1 is 28. So you see this has become equality. Also, these U2 plus U3 minus V2 minus V3, 1 plus 25 minus 1 minus 0, 25. U3 minus V3, 25 minus 0 is 25. Minus U3 plus V2 plus V3 also becomes minus 24. So you see, we get out of 6 constraints, 4 constraints have turned to equality, and 2 constraints have, they are not turned to equality. So with this fact that 4 constraints have turned to equality and remaining 2 did not, what can you observe about the primal variables from the complementary slackness condition? What can you infer? Please remember that complementary slackness theorem says that if the dual slack vanishes, right? If the dual slack vanishes, that means the corresponding dual constraint turns to equality, the primal variable will exist. That means there will be a value in the primal variable. It will not become 0. It can still be 0 if it is a degenerate solution, but at least it will be in the basis. All right. So also one can see another interesting thing. The remaining equations, you see, this becomes, there is a dual slack that exists, here. So if the dual slack exists, that means non-zero, that means the corresponding primal variable has to be 0. So not only we know that there will be some value of y1, y2, y3 and x2, but we also say that x1 and x3 are going to become 0. Look here. So this is, let me read out that simple statement of the complementary slackness condition at one more time. In fact, the second statement is important. If at an optimal point the dual slack vanishes, the dual constant turns to equality, then the corresponding primal variable exists in the basis. Yes or not? The other statement was if the primal slack vanishes at the optimal point, the primal constant turns to equality, then the corresponding dual variable exists in the basis. So these complementary slackness condition, if we apply at this point of time, uh, not only we see that x1 and x3 will turn to 0 because there is dual slack. See, if dual slack exists, primal variable turns to 0, and if dual slack vanishes, the corresponding primal will exist in the basis. So these actually tells that y1, y2, y3 and x2 will exist, and x1 and x3 will turn to 0. So is it understood by everyone that really complementary slackness condition has been used here, and these come at the optimal point, and we already seen the optimal solution for the dual, and that has actually helped us in deriving or understanding certain interesting thing about the problem. So is it clear to all of you? See, the complementary slackness condition states that if at the optimal point the primal slack vanishes. So you see, the primal slack into the corresponding dual variable or the dual slack into the corresponding primal variable equal to 0. So you must remember that equation. Equation is very simple. Primal slack multiplied by corresponding dual variable equal to 0. Is it not? So if primal slack does not vanish, if primal slack exists, that means there is a value, then the corresponding dual variable will become 0. That is one assumption. And if the primal slack becomes 0, then the dual variable will have a value. Now it can be 0 also, because 0 into 0 is also 0. But one thing we can say that it will be in the basis, right? So it will exist in the basis. Now while it exists in the basis, it can also have a 0 value in case of degenerate solution, but at least it will remain in the basis. All right, so these are the things. So having said that, we have seen that x1 and x3 will turn to 0 because of the dual slack, because dual slack exists in 4 and 6. So therefore the corresponding primal variable will turn to 0. So we found x1 equal to 0 and x3 equal to 0. Now additionally, there is one more very interesting thing. Look, the dual solution u1, u2, u3 and v2 exist. So u1, u2, u3 and v2, these four, the first three and the fourth, those four exist, and v1 and v2, v3 become 0. So you see, if the dual variable exists, then the corresponding primal slack will now turn to equality. The primal slack will become 0. So look at the first equation. U1 exists. We know that U1 into primal slack. So these are the primal problem. So U1 exists. U1 has a value. U1 multiplied by the primal slack. So Y1 plus S1 equal to 200. So that means U1 S1 equal to 0. Now if U1 S1 equal to 0 and U1 has a value, then S1 must be 0. So if S1 equal to 0, can you say that then Y1 equal to 200? Please look at carefully. See, again, U2 has a value, and suppose in the second constant the slack is S2. So we know that U2 into S2 equal to 0 and U2 has a value equal to 1. So what that tells about S2? S2 becomes 0. So that means the second constant also turns to equality. What about the third constant? U3 has a value. So the third slack is S3. And again we know U3 S3 equal to 0. And U3 has a value. So S3 also will become 0. That means this constant will also turn to equality. And same thing, since V2 exists, the fifth constant will also turn to equality. All right. So you see, from the dual solutions, we could understand so many things. First of all, we could interpret the dual. We can also interpret the primal. All right. Earlier we have interpreted the dual. Here we have interpreted the dual, and since some of them become equality, therefore we know those primal variable will exist, and some of them that did not equalize, they remain, the dual slack still remains. From there we could infer the corresponding primal variable has to become 0, because in this fourth one, if the corresponding surplus variable S4, or maybe we can call SS4, so minus SS4, so SS4 into X1 equal to 0, and SS4 has a value, so X1 has to be 0. Similarly here, from the last one, we could say X3 equal to 0. So X1 equal to 0 and X3 equal to 0, that is what we inferred here. And now what we are inferring from the primal problem, since the dual variable exists, so primal slack will vanish. All right, so look here, this is exactly we are written here, that we found that the primal variables y1, y2, y3 and x2 are going to exist, isn't it? And x1 and x3 will turn to 0. This is what we saw from the dual. But now from the primal problem, since u1, u2, u3 and v2 exist, corresponding primal constant will turn to equality. This is shown in red. So you see y1 then equal to 200, y1 plus y2 minus x1 is equal to 200, y1 plus y2 plus y3 minus x1 minus x2 equal to 200, and x1 plus x2 minus y1 minus y2 will now become 300. So also we knew that x1 and x3 become 0. Now can you tell me, if those facts are already known, that these are equality and x1 and x3 are equal to 0, can you from there tell very clearly what should be the value of y1, y2, y3, x1, x2, x3? Can you work them out now? You see y1 equal to 200. What will be the value of y2? Because y1 is 200, x1 is 0, so y2 is also going to be 0. So exactly that is what I said earlier, that something remains in the basis. That doesn't mean that it has to have a value. The only thing that you can infer, if the dual slack vanishes, that the primal variable will exist in the basis. Only thing, because that it is not directly become 0. But since the variable into the slack equal to 0, if the slack is 0, the variable may exist, may not exist. But if slack is having a value, then that variable has to be 0. All right, so these must be understood in a very clear manner. All right, so therefore, we could find this kind of solution, that is y1 equal to 200, y2 equal to 0, x2 equal to 500 and y3 equal to 500. Why? Because from the first constant y1 200, that's clear. From 1 and 2, y2 equal to 0, that also you have said. Now look at number 5. So in number 5, already you said that y1 200 and y2 0, and we also know key x1 equal to 0. So x2 minus 200 minus 0 equal to 300. So therefore x2 equal to 500. Right? So x2 also we become 500, and from this third constraint, y1 0, y1 200, y2 0. So 200 cancels both side. So y3 minus x1 minus x2 equal to 0, and x2 is 500, x1 is 0. So y3 minus 500 equal to 0. So y3 equal to 500. All right, so that is the solution. We can get that y1 equal to 200, y2 equal to 0, x2 equal to 500, and y3 equal to 500. Is it not? So that is how the complete solution is here. Selling quantities y1 equal to 200, y2 equal to 0, y3 equal to 500, and buying quantities x1 equal to 0, x2 equal to 500, and x3 equal to 0. And what will be the value of z? 28 into 200, 25 into 500 minus 24 into 500. That is 6100. So look here, a slightly complicated problem we could solve simply by inspection. That is how the duality can actually help us. Is it okay? Now, having said all that, yes, duality can definitely help us in solving certain problems of a certain nature. But what can you say about some generalized nature of such problems? The generalized nature of such problems, you see, that is where we have a certain other kind of consideration, particularly with regard to the network problems. The network problems on the other side is, you know, let us say we consider a specific, let's say a transportation problem. So let us say that we have a specific, network simplex method. So let us say we have a transportation problem, and let us say that we have to solve that with a network simplex method. So let's say that we have the supply demand consideration, that the supply to demand is 2 per unit, and supply 2 to see, let us assume this way, that there are 2 supply points and there are 2 demand points, and availability at the first supply point is 20, availability at the second supply point is 60, and the demand values are 40 in this two particular thing. So you can see that, first of all, this is the balance problem. Total availability is 20 at this point, 60 at this point, and 40 40. That means 20 plus 60 equal to 80, and 40 plus 40 equal to also 80. So the cost of transporting material S1 to D1 is 2, S2 to D1, S2 to D1 is 1, and S1 to D2 is 2, and S2 to D2 is also 2. So therefore, we see that these particular transportation problem, we can start with an initial solution, and that initial solution, let us say, is the starting solution, that we say that we supply something from S1 to D1, S2 to D1, and S2 to D2. Is it all right? So that value, let us say, we say that we send 20 units from S1 to D1, 20 units from S2 to D2, and 40 units from S2 to D2. All right. So the initial solution, let us not get into those details, because there are lots of things you do not know. So only thing that you can tell here, that we have an availability of 20 in the first supply point, and we supply 20 to the first distribution point, and we have the another 20 from S2 to D1 and another 40 from S2 to D2. So that actually perfectly balances. First of all, these 20 units here, and 20 plus 40 units, 60 units. So that is all perfectly balanced. So this is an initial solution, but we do not know whether this particular initial solution is an optimum solution. You see, what you can do, I know you can actually therefore from here, try to find out a dual of the problem. And you know what the dual problem essentially become. The dual problem essentially will come out to be the node potentials of these four different nodes, right? And you see, we have to look at the current solution which forms a spanning tree. We do not really know what is spanning tree at this point, but at least this much we know, that the current solution, that is S1 to D1, S2 to D1 and S2 to D2, that current solution will constitute our current solution, and from there we can find out the node potentials. So how to find out the node potentials? Now when we talk about node potentials, the node potentials are nothing but they are coming from the cost. Why they are coming from the cost? Because you see, the original problem, if you formulate, the original problem would come that the total amount supplied from S1 and S2 to this D1 has to be less than 40, and total amount supplied to this has to be 40, and total amount supplied from S1, that means these two sum should be 20, and the other two sum should be 60, isn't it? So from those equations, if you take the dual, and those dual will actually correspond to these node potentials. Okay, I'll answer those. Now you see what you can do, you can therefore let us go to here. See, look here. Now what we can do, we can find out the cost potentials equations in this way. S1 minus D1 equal to 2, S2 minus D1 equal to 1, and S2 minus D2 equal to 2. Right? So these cost potential equations, that would give the node cost potentials of S2 equal to 2, D1 equal to 1, S1 equal to 3. Put D2 equal to 0. So what exactly we have done about these node potentials? See, our initial solution is S1 to D1, S2 to D1, and S2 to D2. What we have done, is we assume that, because that's what comes from the dual problem. The dual problem essentially gives us that each of them from the cost point of view, because cost of transporting from S1 to D1 is 2 units. So and S2 to D1 is also 1 unit, and S2 to D2 is 2 unit. So that would give us, from D2 to S2 and S2 to D1 and D1 to S1. You have to follow the arrows. Those differences are equal to the cost values. Where from these constants are coming? These constants are coming from the dual equation. So the details are not shown, but that would actually compute the node potentials. So what you can do, the solution, that is, see, this is like the basics. The basis at this point is represented by S1 to D1, S2 to D1, and S2 to D2. So S1 to D1, if we really to compute the Cj minus Zj value, that you can then compute from the node potential. Because look here, that what is the node potential for S1? Node potential for S1 is 3. What is the node potential for D2? It is 0. So that means these S1 minus D2, as far as the Z value is concerned, that means Zij, that should be equal to 3. And what is the corresponding cost per unit? Cj? Cj is 2. So that means that 2 minus 3, that will be the Cj minus Zj for S1 D2. So how it will help? It will actually help us in finding the, what you call, S1 minus D2. That means it is going to be a profitable arc, and it is meaningful to send some material from S1 to D2, which can then be further exploited. Is it all right? So, I know very quickly I wanted to tell a little bit of an example of how network simplex method can actually be employed and how network simplex method can try to solve transportation problem, and particularly how duality can actually help us. Is it all right? That will be today's presentation. So I stop at this point.